So what happens if a car drives slower, say at 30 kilometers per hour? If the car is moving too slowly, it will naturally tend to slip down the bank. To prevent this downward slip and hold the car up on the bank, we need a friction force acting on the incline. So we need to find the minimum coefficient of the friction that is large enough to keep this slower car from sliding. In this case, we need to redraw our free body diagram to include the force of friction. We still have the gravitational force Fg pointing down and the normal force Fn, which is perpendicular to the surface. But now we have the friction force Ff points up the bank because the car's tendency is to slide down, right? And we still have our xy coordinate system. At this time, we need to decompose both Fn and the new friction force Ff. Both of them are angled, right? We'll follow the same process using the right angled triangle. Starting with Fn, we have its Fnx, and this is Fny. This angle is theta, and this angle is theta. So Fnx is the opposite side of the angle theta. Fn sine theta. And the vertical component, Fny, is Fn cosine theta. Fny is the adjacent side of the angle, right? Now for the friction force, we create a right angle triangle like this. So this is the horizontal component, Fx, and this is the vertical component, Fy. So this angle is theta. So we have Fx component. It is the adjacent side of the angle theta. So it equals to Ff cosine theta. And the y component, Ffy, is the opposite side of the angle theta. So we have Fy equals to Ff sine theta. Now all the forces are along either x or y axis. So we are ready to find the net forces. Okay, starting with the vertical direction, F net y. The forces pointing up are Fny and Ffy. And the only force pointing down is this gravity. So we have F net in the y direction is Fny plus Fy, then minus Fg. And looking at our decomposed forces, we have Fny is Fn cosine theta plus Ffy is Ff sine theta. Then minus Fg is mg. Now we know Ff equals to mu Fn, right? We can substitute that in, giving us Fn cosine theta plus Ff is mu Fn sine theta minus mg. And we know the car is not accelerating vertically, so F net in the vertical direction is 0. So those upward forces balance the gravity, right? So rearranging this equation, we have mg equals to Fn cosine theta plus mu Fn sine theta. We can factor out this Fn, so we have mg equals to Fn cosine theta plus mu sine theta. Now let's look at the horizontal direction, F net x. It equals to the horizontal component of the normal force Fnx is pointing towards the center of the curve. And the friction force, Fx, points away from the center, right? So when we put them together, it's going to be the subtraction of these two components, right? So we have F net x equals to Fnx minus Ffx. So Fnx is Fn sine theta minus Ffx is Ff cosine theta. And we know this net force in the x direction provides the centripetal force needed to turn the car. So F net x equals to Fc. And again, by definition, Fc is mv squared over r equals to Fn sine theta minus Ff is mu Fn cosine theta. Now if we factor out the Fn, we have mv squared over r on the left side and Fn bracket sine theta minus mu cosine theta. Again, now we have two equations. This is equation 1 and this is equation 2. And now if we divide equation 1 by equation 2, on the left side we have mg from equation 1 over mv squared over r from the equation 2. On the right side we have Fn cosine theta plus mu sine theta from equation 1. And the bottom we have Fn sine theta minus mu cosine theta from equation 2. Again, by doing this, we can eliminate Fn and the mass m. And after simplifying the left side, we have g multiplied by r over v squared equals to cosine theta plus mu sine theta over sine theta minus mu cosine theta. The final step is just to plug in all the values so we can solve for the coefficient of the friction mu. Okay, from our previous calculations, we know the banking angle is 12.1 degrees. So on the right side, we have cosine 12.1 degrees plus mu sine 12.1 degrees over sine 12.1 degrees minus mu cosine 12.1 degrees. And on the left side, we have g is 9.8 meter per second squared multiplied by the radius, which is 180 meters, over the speed. So the speed is 30 kilometers per hour. And after dividing it by 3.6, it converts to 8.3 meter per second. So the speed is 8.3 meter per second, then squared. So the left side works out to 25.6. It equals to cosine 12.1 degrees is 0.98. Sine 12.1 degrees is 0.21. So we have 0.98 plus 0.21 mu over 0.21 minus 0.98 mu. To solve for mu, let's get rid of the fraction by multiplying the denominator on both sides. So we have 25.6 multiplied by this denominator, 0.21 minus 0.98 mu equals to 0.98 plus 0.21 mu. Now we can remove the brackets by multiplying this 25.6 with these two values in the brackets. So we have 5.376 minus 25.1 mu equals to 0.98 plus 0.21 mu. Now we want to gather all the terms contain mu on one side and the constant numbers on the other side, right? So rearranging this equation, we have 5.376 minus 0.98 equals to 25.1 mu plus 0.21 mu. So the left side is 4.4 and the right side is 25.31 mu. So this gives us mu equals to 0.17. So to allow the car to drive safely at 30 kilometers per hour and prevent it from slipping down the bank, the road surface needs a minimum coefficient of friction about 0.17. And this ensures the surface has enough friction to provide the necessary outward force to hold the car in the circle. Okay. Finally, let's look at the case where the car is driving faster than the design speed and traveling at 90 kilometers per hour. What happens here?